Greetings and welcome to my new calculus channel. My name is John Gabriel. So in a previous video, I talked again about these trigonometric, closed form trigonometric formulas, which nobody else had realized before me. And I got a question from a user, and this is his question on this page. He said, I just went through the document, and he says, your definition of angle is based on the idea of ratio of magnitudes. Well, that's not quite correct. It's based on the measure of a ratio of magnitudes, which in this case would be the measure of, let's move this along here, of the distance along the hypotenuse to the hypotenuse, okay? So, and we simply write d since our hypotenuse is the unit. Then he says, you then provide formula to convert from the radian convention. No, he misunderstood this because that's not what I did. In order to do this, you need Hippias and Hippias's kinematic curves. Okay, so you can't do it with. Well, you could do it using algebra, but that and Cartesian systems, but that came many years later. The Greeks didn't have that back then. So then, of course, it says if I got it right, I'm generally impressed, etc. So, all right, let's see how I responded. So I said. The first understanding is correct. It's simply a distance d along the hypotenuse. And of course, the formula I provide do not work with radians or degrees. They work strictly with radical angles. They're more accurate, they're easier to use, and they're much faster because the trigonometric functions are closed form. So how do they basically work? Well, let's see very quickly how they work. So initially, you would have used a circle, right, with a right angle in it, like this, right? A circle with a right angle, this right angle here. But we don't need that. We just need a right angle, meaning that this side, isosceles right angle, meaning that that side is equal to that side, and we choose any distance along here. So if we had, let's say that distance, we draw a vertical down here. And of course, this little triangle would be similar to the big one, meaning that that distance is equal to that distance. Now, what we want to do is we want to, using this distance, find a parameter, either one of these distances, which will enable us to find the lengths of the hypotenuse, the adjacent, and the opposite. So let's draw a clean one here, like that. If we do that, and that's the distance along there, and that's x. If we join this line up here, that's also x, meaning that's 1 minus x. And this distance here is root of 1 minus 2x plus 2x squared, all under the radical. So we've got everything we need, opposite, hypotenuse, adjacent, right? And then we use this x as a parameter. Okay, what does that mean? That means using this distance, we say d squared is equal to 2x squared, meaning that x is going to equal to d over root 2. Right? So this is our angle here. D is our angle. So we always divide D by root 2 to get the parameter. And I'll show you how to use that parameter in all the functions because it is used in all the trigonometric functions that I'm going to show you. So let's see if this article has been loaded. If not, I'll reload it. But if we look at academia here and go to my profile, and we go down to the article, let's see if we can get it. If we can't, I'll upload the text version. I should have done that already, but okay, let's see if we can load it now. Loading preview, hello. All right, I'm not going to waste time on that. Let's just go here and load it this way. There we go. So now those formulas are all very simple and they're all stated down here. I'll show you now. Okay, here we go. So here are the simple formulas. Oops, still not there yet. All right, where is it? I think I went too far back. All right, let's just load here. Goodness, badness. All right, here they are. So trigonometric functions, here the the ratio functions on the left and the angle or the inverse functions, which find the angle, which find the find the angle from the ratio. Okay, so the parameter here is, and by the way, it's the same. So you don't have to worry about converting between degrees and angles. It's all very simple because everything is done in terms of one length. So you're not switching between different types of magnitudes. Just remember that. That's very important. Okay, so now that I've explained that, um, the next step I want to talk about is the fact that you only use this Hippias kinematic curve if you want to find corresponding measures in radians or degrees. Okay, so the new functions use exactly the same definitions. So, for example, let's clear this. You would still say it's this opposite over adjacent and hypotenuse, and very simply, in today's uh, classes, they teach this wrongly. You don't even have to bother with opposite and adjacent. Just use that point on the circumference, which is x, y, and r. Those are the three you need. And for example, I mean, if you try to draw a right angle there for sine 90, there is no right angle there because you don't have x. Okay. Similarly, if you have cos 0, there is no right angle because you don't have y. Right. So it's all just y over r, x over r. These are the definitions. Right. Then that was the second point I wanted to make. And then if you wanted to find, let's say, 3/4 of a right angle, how would you do that? Okay, so you can't just say 3/4 of square root 2, right? So 3/4 of a right angle is not just 3/4 times square root 2. That would be wrong. And if you think about it in terms of degrees and you say 90 degrees divided by 4, I'm sorry, 90 degrees divided by 4, that's approximately 22.5. And if you multiply that by 3, you'll have 67.5 degrees, okay? So this is 22.5 degrees, and you multiply it by 3. And now, you can't use this with the new functions unless you use Hippias, because you haven't used right angles. You've used degrees or radians. You use degrees or radians over here, okay? So what you do is you would come to your Hippias diagram, choose 4 partitions like that. Oops, 4. And then you would move it 3 times. 1, 2, 3. And note that the length there is 1. So that would be your angle, okay? And you would come along here and you would say, let's say you want to find the sine. Then you would say the sine of angle 1, right? I'm sorry, I made a mistake there. No, what did I do? It's not the sine of angle 1. It's angle 1 divided by square root 2, which is this one that I've already done here before. I'm sorry, I've done it. Here it is. So this would be the ratio, 0.923879, right? That's the ratio. And of course, you can check it using degrees by going to a calculator or any other package and saying it's in degree mode, choose 67.5, take the sine, and yes, it corresponds, 9238795. There it is, okay? So that's how you would, for example, if you don't know the right angle measure, you could find it using Hippias, this diagram here. So you'd put your partitions in here, and then it would give you the length of the sine line segment, which you divide by root 2 to get the parameter, okay? You always divide that sine line by root 2 to get the parameter. So the next point I want to make is that if, for example, you had 120 degrees, so let's say you had 120 degrees, let's reset the canvas, confirm. Hope I'm not going too fast, but where's my pen? Right. So if you want the sine of 120 degrees, like that, that would be the same as saying the length of the hypotenuse minus 1 right angle, right? Or 1 partition length, I'm sorry, 1 partition length, because 120 is the same as 4 times 30, right? So you would come back here and you would say 3 like that. Go back to the beginning here. And one partition would be 51674. So this would be your angle, okay? In other words, you would find your sine 120 by saying sine of root 2 minus 0.51764 approximately all over root 2, okay? So why this? Because this is equal to 30 degrees and we're subtracting it from this and we're automatically getting the corresponding value if it's 120 degrees in the second quadrant, okay? So, and how do we know that's true? Well, we go again to a package like I did here and I calculated and it's 0.8660. And if you go to your calculator and you type 120 and you look at the sign, it's correct. Okay, it's 0.8660254. Right. So you won't need Hippias at all if you stay with radical angle units. It's not like Newton's, for example, where you have infinite series which are never accurate. With these radical angles, you always have the correct measure, right? And you can get used to working with radical angles and recognize them by realizing that 30 degrees, if you want to have a comparison, is approximately 0.51764. 45 degrees is root 2 over 2 or 1 over root 2, which is equal to approximately 0.717. 60 degrees will be approximately 0.89658. Now remember, these measurements that I've given you here are the length of this segment here, okay? This line segment. And 90 degrees will be root 2, okay? So that's how you would recognize more or less what they are, but you don't really need to use degrees or radians, which are a lot more complicated. So finally, the last thing I'd want to mention is that in ancient Greece, they had this information long before Euclid or Archimedes, and even possibly Hippias, because they were able to create fluted columns. So if you look at these columns, they've got like little dents in them. So what I mean is this. So if you have, let's say, something like that, you need to be able to determine how to divide those up into angles. And then, of course, the architecture would remove this bit of the marble, and then you'd get that lovely fluted architecture, where these are, actually it's that way, where these are all sort of dipped in to the marble. Okay, so that's pretty much it. I hope I've explained everything. I think I've covered all the points I wanted to. I tried this before and the sound was off, so this is the second time I'm doing it. If you're not already a subscriber, become a subscriber. I'll give you a link to all these articles and applets, and tell your friends about this. Click like, and I'll be chatting with you again soon. My name is John Gabriel, and this is a new calculus channel. Till next time, goodbye.